Today we're going to start talking about energy, and in this section we're going to talk about energy, work, power, and mechanical energy. Most of the calculations are in these sections. In the next lesson we'll also learn about the work energy theorem and conservation of energy. Those also require some calculations. And then we'll talk about the concepts of machines and efficiency and recycled energy and energy for life. So these will be in the next lesson, and today we'll be talking about the first four. Okay, so the first thing we need to understand is what energy is. Well, first of all, the universe is made up of energy and matter. And so those two things make up everything in the universe. So what actually is energy? Energy makes things move. It's the mover of substances. It is also both a thing and a process. What that means, we can talk about it as a thing, it's a mover, and it's a process, it's something being done. So when do you observe energy? You observe energy when it's being transferred. So for example, if you see a car crash into a wall, you see energy being transferred from kinetic energy to heat and sound. Or when that's actually being transformed. I'm sorry, that's energy being transformed from one form to another. When it's being transferred, that's like last chapter when we saw a cue ball hit another cue ball and the first one stayed still and the second one started moving. That was a transfer of energy. And it's a conserved quantity. Energy can be neither created nor destroyed, but it can be transferred and it can be transformed. But all of the energy you started off with is energy you end up with. So the usual definition of energy is the property of a system that enables it to do work. We haven't talked about what work is, but this is the fundamental definition of energy. It's the property of a system that lets it do work. Also, any kind of energy can be turned into heat. Any kind of energy at all can be turned into heat. So one example is electromagnetic waves from the sun. Electromagnetic waves include the light, visible light that we see, and other light like UV light, ultraviolet light, or infrared light. And when those hit the earth, you can see that the earth is going to heat up. And so you can see that that must be some type of energy because it gets turned into heat. Now, what's the difference between energy and matter? Matter is substance we can see, smell, and feel. So that's pretty straightforward. A table is matter. A computer is matter. And it takes up space. So that's what matter is, and that's how you can distinguish it from energy. Okay, work. Here's going to be our first formula, is that work involves force and distance. So work equals force times distance, or in an equation form, W equals FD, force times distance. So this is an equation you should know. You do work anytime you apply a force over a distance. Now remember what a force is. Force is measured in newtons, and a force makes something accelerate. If you remember the definition for force, force was mass times acceleration. So when do you apply a force? You apply a force when you have a mass, something made up of mass, and you're accelerating it over a distance. So two things have to occur whenever work is done. One thing is you have to apply a force, and the second thing is there has to be some movement by that force. So if there's no movement, no work, no force, no work. So for example, if you push against a stationary brick wall for several minutes, you do no work because the wall is not moving. So if you push against a stationary brick wall for several minutes, you do no work on the wall at all, both of the above, or none of the above. What do you think the answer is? You do no work on the wall. So why is it no work at all? The reason it's not no work at all is you may do work on your muscles. Your muscles may move. If you look as you're pushing against the wall, you can see your muscles move. So you may be applying a force on your muscles, but you're not doing any work on the wall at all. If you do twice as much work if you lift 2 loads 1 story high versus 1 load the same distance. So let's take a look at that. So here we have someone moving 1 mass 1 story. Here we have someone moving 2 masses 1 story. So that means this person has to be applying twice the force. And if you remember the definition for work, I'll get there. Oh, wonder what all that is. I am not going to worry about it right now. Okay, so let's think about our definition for work. We said that work equals a force times a distance. Now, we had our first example where we lifted 1 load up a distance. And then we had another example where we lifted a load that was twice as big up the same distance. So since it doesn't matter what the distance is, let's just say this distance is 1, and this distance is 1, and this load is 1, and then this load has to be 2. So how much work do we do in the first instance? Well, to lift a load of mass 1, that force is going to be the mass times g, which is the acceleration times gravity. So our force is going to be 1 times 10. So anytime you lift a mass, your force will be the mass times g. Why don't we write that? Okay, lifting a mass. Whenever you do that, your force is your mass times g, and we usually use 10 for g. So that's where this force comes from. Now, what distance did we lift it? We lifted it a distance 1. So the work that we did was 1 times 10 times 1, which is 10. Now, in our second example, work still equals force times distance, and our force is m times g. So it's our mass, which now is 2, times g, which is 10, times our distance, which is 1, which is 20. So we can see that when we lift twice the mass, we do twice the work. Okay, so the reason was the force needed to lift twice the load was twice as much. Now let's take a look at a different example. Here we're going to lift 1 load 2 stories. So let's take a look and see what the difference is there. Okay, so in our first example, we're going to lift 1 mass 1 story. In our second example, we're going to lift the same mass 2 stories. So let's just call this mass 1 and this mass 1 and this distance 1. Then this distance will be 2. Now remember, when you're lifting, your force equals m times g. So in our first example, the work equals the force times the distance. Now because we're lifting, Our force is mg. Our distance is going to be how high we're lifting it. So our work will be 1 times 10 times 1, which is 10. And our second example, we still have force, work equals force times distance. Our force for lifting is going to be mg times our distance. Our mass is 1, g is always going to be 10, but here our distance is going to be 2. So our work will be 20. So if we go twice the distance, we have twice the work. So we learned twice the force equals twice the work, or twice the distance equals twice the work. Now, what do you think would happen if we lifted twice the distance and twice the force? So if I added another one here, what would happen? Well, we'd have twice the work because we had twice the force, and then we'd have twice again the work because we had twice the distance. So our work would end up being 4 times as much if we doubled the mass and doubled the distance. By the way, if we look at our units here, the units of force are newtons. So that's this one. That's our units of force, and those are newtons. Our units of distance are meters. So the units for work equals a newton times a meter. And we have a special name for that. We call that a joule. So a joule is a unit of work, and we'll find out later that work is, when you do work, then you are changing energy, so it's also a unit of energy. So in this instance, we did twice as much work when we lifted the load 2 stories instead of 1 story. Okay, so let's look at an example. The weightlifter lifting the barbell from the floor does work on the barbell because he is lifting a mass a distance. Now here's what we were talking about with the unit of work. You have a force times a distance, or a newton times a meter, and the other name for that is a joule. So work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy, the same distance? So think about our examples. We're lifting the barbell twice, it's twice as heavy, but the same distance. How much work are you doing? Twice as much, half as much, the same, or it depends on the speed? And the answer is twice as much, because it's twice as heavy. That means you have twice the force, and so the work will be twice as much. And so that's from the formula, work equals force times distance. Twice the force means twice the work. You do work when pushing a cart with a constant force, so you are applying a constant force. If you push the cart twice as far, then the work you do is less than twice as much, more than twice as much, or 0. It'll be twice as much, because remember, when you if you do twice the distance, then you have done twice as much work, because work is force times distance. So if you have force times distance, then if you do twice the distance, the work is twice as much. Okay, now let's talk about power. Power has to do with how fast the work is done. The amount of work you do doesn't depend on the power, that doesn't depend on how fast you do it at all. But power does depend on how fast you do it. So power equals work done over the time interval. So this is the formula you need to know. Power equals work done over time interval. So let's write that. Power equals work over time. Now, if you remember with the fraction, if the denominator is bigger, then the total answer is going to be smaller. And if the denominator is smaller, then your total answer will be bigger. Let's look at an example of that. Let's look at 1/2 versus 1/3. Which one is bigger? This one is bigger, but it has a smaller denominator. So a smaller denominator means the overall thing is bigger. So more time equals less power. Less time equals more power. And that makes sense if you think about it. If you lift something heavy quickly, then you've used more power. And if you lift something heavy but you go slowly, then that corresponds to less power. Well, now let's look at our units here. So the units for power. It'll be the units for work, which we just said were joules. Remember that? The units for work are joules over time. So that's the units for power, joules over time. Now, this isn't a formula. This is just telling you the units. And we have a special name for joules over time. We call that watts. Okay, so how fast work is done depends on the work that's done and the time interval. So if you think about the space shuttle lifting off, when you look at it, it actually doesn't take, it actually takes like 2 or 3 seconds to get up to here, but then you're doing a lot of work because this is a really big mass. Okay, so here's our example. A worker uses more power running up the stairs than climbing the same stairs slowly. The work would be the same because it's the same mass, same distance. Doesn't matter for work, doesn't matter how fast you do it. But for power, you use more power if you go quickly than slowly. Now let's think about this engine here. Twice the power of an engine can do twice the work of one engine in the same amount of time. So here, if you have an engine, it can do twice, an engine that has twice the power can do twice the work in the same amount of time. Let's see why that's true. So power equals work over time. So power times time equals work. So if we had twice the power in the same amount of time, same time, so twice the power, same time, you could do twice the work. Does that make sense? So you double this, you double this. So twice the power of an engine can do twice the work of one engine in the same amount of time. Or twice the work of one engine in half the time, or at the rate at which energy is changed from one form to another. Okay, so let's look at that. Okay, so let's say we have one engine, I'm just calling that an engine, and it has power 1. And I have another engine, and it has power 2. So this one has twice the power. Now we said in the same amount of time, it could do the same amount of work. Well, now let's look at half the time. So this one will operate for 1 second. This one will operate for half a second. Okay, so let's look at this one. We know that work equals power times time. You might want to write that down. That's just a restatement of this one, but it might be helpful. So work equals power times time. So here our work is 1 times 1, or 1, and let's just say that we're using standard units here. So 1 watt. Work is in joules. So 1 joule. Here, work equals power times time, or our work, our power is twice as much, so we'll say it's 2 watts. Our time is half as much, So 2 times 1/2 is also 1 joule. So they can do, if I have an engine that has twice the power, it takes it half as long to do the same amount of work as an engine that has half the power. So if you have twice the power, it takes you half as long to do the same amount of work. Now the unit of power is a joule per second, and we said that was called a watt, and it's named after someone named James Watt, who was the developer of the steam engine. So 1 joule per second is 1 watt. We also talk about a kilowatt, which is 1,000 watts. So a job can be done slowly or quickly. Both may require the same amount of work. So for instance, if you lift a mass a certain distance, doesn't matter how long it takes to do, that would be the same amount of work. But if you do it slowly or quickly, it might require different amounts of energy, momentum, power, or impulse. Now notice the only thing that's changing here is the time. So which of these is going to be different? And the answer is power, because power is the one, if you do the same amount of work but in different amounts of time, that's going to be different power. So power is the rate at which work is done. That's a good definition of power. You might want to write that down if you don't already have it. Power is the rate at which work is done. Okay, now we'll talk about mechanical energy. Mechanical energy is due to either position or motion or both. So mechanical energy is energy due to position and motion. So you have to look at both of those to get mechanical energy. And there's 2 forms of mechanical energy. You have potential energy and kinetic energy. You've almost certainly heard of both of those before. But both of these are forms of mechanical energy. First, we'll talk about potential energy. Potential energy is stored energy held in readiness with the potential for doing work. If you remember, one of our definitions of energy was the capacity to do work. So if you have stored some energy and it's got a potential to do work, that's potential energy. So we'll look at a couple examples. You've stretched a bow. So you stretched the bow and you have an arrow on it. That has stored energy that can do work on the arrow, because if you let go, that stretched bow will make the arrow move. Another example is a stretched rubber band of a slingshot. It has stored energy, and because of its stored energy, it is capable of doing work. If something is raised up high, it has the potential to do work. Because, for example, if it's raised up high and you let it go, then as it falls down, it can do work. So example is water in an elevated reservoir. So if you store water up high, then as it comes down, it can do work. It can like turn a turbine or something like that. The raised ram of a pile driver. So a pile driver is something you can use to knock something into the ground. You raise it up high, and then as it drops down, it can knock that nail or whatever into the ground. So potential energy equals the work done, which is, so you do some work to raise it up, the force required to move it upwards, times the vertical distance moved against gravity. So in equation form, so here's the equation you need to know. The potential energy, this is gravitational potential energy, that's what we call it, gravitational potential energy, is mass times acceleration due to gravity, because that's the force we needed to apply to move it up, times its height, or simplified, mgh. So if I want to look at gravitational potential energy, so what is the gravitational potential energy of a 10 kilogram cat 5 meters above the ground? That's pretty high up, but you know. Okay, so here I have my cat. This is 5 meters. Of course, we know this is a special flying cat, so when he gets to the ground, he can fly off. Okay, so what is the potential energy of this cat? So gravitational potential energy. Now this cat has gravitational potential energy. Particular a lot, that's a great phrase. Gravitational potential energy, because he's a fairly massive cat. Gravitational potential energy is mgh. So mass of the cat, 10 kilograms. Acceleration due to gravity, we usually use 10 meters per second squared. The height is 5 meters. So 10 times 10 is 100, times 5 is 500. So that's 500. And our units, kilogram times meters per second squared, is newtons. Newtons times a meter is a joule. Or you can just remember energy is always in joules. So gravitational potential energy is 500 joules. Does a car hoisted for repairs in the service station have increased potential energy relative to the floor? So it was on the floor and then it gets raised up. And the way this happens is you have an air compressor. The air compressor pushes down into this reservoir, and that's going to push the piston up, which is going to raise the car. So that's how it gets moved up. And so does this car have increased potential energy relative to when it was on the floor? And the answer is yes, because it has been raised a distance. And we know that potential energy, gravitational potential energy, so gravitational potential energy equals mgh, that's the height. So if the height is bigger, you have a bigger gravitational potential energy. If the car were twice as heavy, its increase in gravitational potential energy would also be twice as great. So let's look at that. So if instead of making this twice as much, we made this twice as much, we would still increase the gravitational potential energy by twice as much. Okay, here's another example of potential energy. Here, we've lifted a ball straight up 3 meters. Here, we've taken the same ball and we've lifted it up a total vertical distance of 3 meters. Here, we've taken this ball, we've rolled it up a hill 5 meters, but the vertical distance that we've changed it is only 3 meters. So you only look at the vertical distance to figure out gravitational potential energy. How much higher is it? Doesn't matter about the horizontal distance. This one is 3 meters higher. This one is 3 meters higher. This one is 3 meters higher. And if we look at our formula for gravitational potential energy, it depends only on the height. It doesn't matter how far you moved it horizontally. So all three of these have the same potential energy. It's a 10 Newton ball and it's raised 3 meters. So let's look at that. So a 10 Newton ball raised 3 meters. What is its gravitational potential energy? So it said 10 newtons. Now keep in mind, a newton is already mg together. It's a force. They didn't give us the mass. They gave us the weight. So you can also say gravitational potential energy is weight times height. So if they give it to you in newtons, that's the weight. So our gravitational potential energy also equals the weight, and you'll know it's the weight because it'll be in newtons and not kilograms, 10 times 3, because the same ball had the weight 10 each time, the vertical distance was 3 meters each time, so the gravitational potential energy is 30 joules. So be careful with that distance, with the difference between weight and weight and mass. Remember, weight is in newtons. Mass is in kilograms. So we can state the gravitational potential energy in 2 different ways. So you might want to write this down too. Gravitational potential energy equals mgh, and that's the same as weight times height. So if they give you weight, use this. If they give you mass, use this. Okay, now we'll talk about kinetic energy. You probably remember that kinetic energy is the energy of motion. It depends on the mass of the object and the square of its speed. So that includes the proportional constant 1/2 and the mass and the speed times the speed. So if the object's speed is doubled, the kinetic energy is quadrupled. So let's see why. If we double the speed, we have 2 times here and 2 times here. So 2 times 2 times is 4 times. So if we double the speed, we quadruple the kinetic energy. If we double the mass, we're only going to double the kinetic energy because it only appears here once. So let's write a formula for that. So kinetic energy equals 1/2 mass times speed times speed. And let's remember what I said about that. If we double the speed, so we make each of these 2 times, then our kinetic energy will be 4 times because it's 2 times times 2 times. But if instead we only double the mass, so if we make this 2 times, then we have only changed the kinetic energy by 2 times as much. So double the mass, twice the kinetic energy, double the speed, 4 times the kinetic energy. What if instead we made the speed 3 times as much? What would happen to the kinetic energy? It would be 3 times times 3 times. It would be 9 times as much. What if we tripled the mass here? If we tripled the mass here, the kinetic energy would be 3 times as much. Must a car with momentum have kinetic energy? Okay, so let's take a look at that. It has momentum. So now you have to remember your formula for momentum. Momentum equals mass times velocity. If it has momentum, it has to have a mass, and it has to have a velocity. So if it has momentum, it has a mass times a velocity. Now let's remember about what kinetic energy is. It's 1/2 mass times speed times speed. Now if you have a velocity, you have a speed. Okay, now another way of writing kinetic energy, it's a little shortcut, 1/2 mv squared. So 1/2 times the mass times the velocity squared. So if it has a mass and it has a speed, then it must have a kinetic energy. So must a car with momentum have kinetic energy? Yes, due to motion alone. Yes, when motion is non-accelerated. Yes, because speed is a scalar and velocity is a vector quantity. Okay, so let's look at these. And the answer is yes, due to motion alone. Because if we looked at our formula, the kinetic energy was the mass times the speed squared. So it was moving. It didn't care if it was accelerating or not. It still had kinetic energy. So acceleration, speed being a scalar, and velocity being a vector quantity are irrelevant. Any moving object has both momentum and kinetic energy. Any moving object has both momentum and kinetic energy. So kinetic energy and work of a moving object are going to be related, and we're going to talk about that next time.